So we just had a first look at asymptotes when we were looking at infinite behavior. Let's first talk about vertical asymptotes and what those mean. So the line x equals c, so again we are talking about a dotted line just as we saw in our last graph, is a vertical asymptote of the graph as the function f of x, or of the function f of x, if f of x approaches infinity or negative infinity as x approaches c from either side. So that's a lot of like jibber jabber, but here's what it means. As x approaches c from the right, f of x approaches infinity. So on my graph, that would say, as I'm getting closer and closer to c from the right-hand side, this is just getting bigger and bigger, positive infinity. As x approaches c from the left-hand side, if it's approaching infinity, that would look like this. Now, I don't know what's happening down here. It could be that this actually goes more like this. We don't know anything about that. We just know as I get closer to c from the left-hand side, it's going to positive infinity. On this one, we're saying as x approaches c from the right-hand side, it approaches negative infinity. Means, again, it's going to end up going like this, down forever as I get closer to c. Or negative infinity from the left would look more like this. Again, this is not telling me what's happening on these other parts of the function, but that will come later. In order to find those values, we have to determine the real numbers where the denominator is 0, but the numerator is not 0. Let's try this first one together. We're trying to find the vertical asymptotes, and the way that I would go about that is the same way that I would go about restricting my domain. I would set my denominator equal to 0 to find the values that x cannot be, because that's going to help me to know where the asymptote should be. So if I factored this, I would get x minus 5, x plus 1. And what I would look for is to see if anything canceled with the values on the top. In this case, it sure does not, which means that x cannot be 5 and x cannot be negative 1. So where are my vertical asymptotes? Those are going to be the equations of the lines of x equals 5 and x equals negative 1, which means if I were actually going to graph this, I would go to where x is 5, and there's going to be a dotted line there, and where x is negative 1, there would be a dotted line there, where nothing is going to, or where that's where my graph would approach infinity, either from the left or from the right. We have no idea. We'd have to actually do a little bit more work to get to that point, but we know at each of these lines, each of these asymptotes, our function will either go towards infinity or negative infinity. This one's similar. Again, I would set x squared minus 2x minus 3 equal to 0. I would factor this into x minus 3, x plus 1. This one's a little different, however, because notice what happens here. If I put x minus 3, x plus 1, the instructions said it's a vertical asymptote if it makes the denominator 0 but not the numerator. So if I plugged in 3 would make the denominator 0, but it also would make the numerator 0. Whereas if I plugged in negative 1, it only makes the denominator 0. So the vertical asymptotes are only x equals negative 1. So looking at my graph, I would have a dotted line there. What's happening at x equals 3? That means whatever is happening at x equals 3, there's just a hole in the graph. So this is a hole. It is not a vertical asymptote. So there's a hole at x equals 3, and at x equals negative 1, there is actually an asymptote. Last one for you to try on your own, so give it a shot, then press play to check your work. So here again, I would set x squared plus 25 equal to 0. Does that factor? No, it doesn't. Is there any value that would make x work so that this was equal to 0? No. So there's no vertical asymptotes. No vertical asymptotes. There's no value that I could plug in for x that would make the denominator 0.